Hello, my name is Ross Nelson, and I'm with Protocol Insight. Welcome to our demonstration of UFS 3.1 link traffic generation and analysis. Protocol Insight is the market leader for UFS and UniPro protocol analysis and generation tools. We've been shipping UFS and UniPro exercisers and analyzers since 2014, and we've been shipping UFS 3.0 and 3.1 instruments for almost 4 years now. We're the only protocol test tool that can be used to verify compliance to UFSA compliance test matrix, and we've been supporting all of the MIPI, UniPro, and UFSA workshops for interoperability since 2015. In our demo today, we're going to follow the typical chronological test debug sequence. First, I'll talk about connecting to the device under test, including probing options and tools like iMonitor and Smart Tune equalization. Then I'll talk about test setup, including configuring the instrument and triggers and filters. Then we'll capture a trace and we'll go through the analysis of the results. To connect to the device under test, there are several different probing options available. You can use SMA or SMP cables with splitters to connect to your device if you have connectors on the board. You can also design your own breakout DUTs and interposers that will bring signals out using cables like this Ardent cable here. Or you can use solder down probes to solder down directly to individual traces on the circuit. If you're going to be using the instrument as an exerciser, you would configure the exerciser as one end of the link with your device under test on the other side, and you will use SMA or SMP cables to connect the two. Once you've connected to the device under test, you can start to acquire bits on the link to see if you can get error-free capture. If you are getting errors on the link, you can use the iMonitor tool to build an eye pattern of each of the lanes to analyze if you have adequate eye opening. If there isn't, you can use equalization to set attenuation, amplification, CTLE, and DFE settings to open up the eye to ensure that the eye can capture correctly. Once you've determined that you are capturing the link error-free, then you can use the instrument application software to configure and capture traces. The first step with the instrument is to connect the software to the instrument and connect to the device under test. By pressing the connect button, you can see now that I'm connected to the device at PWM Gear 1. Then I will configure the instrument settings. I'll go to the instrument configuration tab and I will verify that for the device, we are capturing at by 2 link width, and for the host that we are capturing at a by 2 link width. Then I will look at the type of memory capture that I'm using. There's 2 types of memory capture that you can use. The standard memory capture will store the trace to the instrument's onboard memory. If you select streaming capture, the instrument will write the trace out directly to the PC over the Thunderbolt 3 connection. I will use the standard memory capture and I will verify that I'm capturing at 128 meg. Now that I've determined that the instrument is configured correctly, I will look at setting any triggers. To set a trigger, I'm going to select the Trigger Setup dialog box. In the Trigger Setup dialog box, you can see that you can choose between No Trigger, Trigger Immediate, Simple Trigger, or Advanced Trigger. If you choose Simple Trigger, you will get a list of packet types on the left side that you can choose from. And you can select from any of those packet types, and if you double click or drag and drop into this section over here, these will be your trigger states. In this case, I will trigger on a data in or a data out. Once you've set your triggers, the last thing you want to do is set your filters by going to the filter dialog. There are 2 types of filters available. We have a pre-capture hardware filter that will filter out packets before they are saved to instrument memory or over the streaming memory capture. The post-capture software filter will capture all the packets, but then it will filter those packets out in the display. With the pre-capture software filter, you can filter out a lot of different types of packets, but the most interesting is message payload. If you filter message payload, we will actually strip out the UFS payload from the packets before we save that. Once you set up your triggers and filters, then we're going to use the exerciser to create traffic on the link. I will go to the mode and I will choose exerciser plus analyzer mode. Then in this configuration window, I am going to choose to run a UFS test 10 times at rate series B on Lund 0 at HS gear 4. And the test that I'm going to run is a read 10 test that generates a series of reads and responses on the link. So the first thing I'm going to do is to start the analyzer. I'm going to boot the UFS device. I'm going to run my stim tests. And now that I can see all of the tests have run, I'm going to stop the analyzer. What you can see down here now is we have packets displayed in the Unipro and UFS packet list. If you go to the traffic overview, you can see that at the Unipro level, we have trig UPR 0s, trig UPR 1s, trig UPR 2s, all the way down to the capability 2 extension. So if you go to the beginning of the trace, you will see the trig UPRs being executed on the link. And then you can see that there are data frame TC0s at the Unipro level. These, of course, are the packets that carry the UFS payload. So if we go to one of these, say the last one in the trace, you can see this data frame TC0. If we put a bookmark on that data frame TC0, and if we go to the UFS packet list and we go to bookmark 1, it takes you to a read 10 packet. So we know that that data frame TC0 was a read 10. But you can see that after that, all the data in packets are listed before you get to a response. There's a lot of data in packets in here, and it would be nice if you could suppress those, because really what we care about is the read 10 and the response. If you come up here to this filter button, you can collapse those data ins. So now you just see read 10 response, read 10 response, read 10 response. The most common thing that people are interested in are the latencies between the packets. So if we put bookmark B1 on this read 10 and we put bookmark B2 on the response, we can see that the latency between the read 10 and the response was 1.05 milliseconds. So you can see the timing of the UFS packets. It would be nice if you could see timing for multiple packets without having to move each individual bookmark. So for that, you can use trace validation. Trace validation is a tool that analyzes a trace and looks for different kinds of information. If I run a trace validation on this trace and I look for a command packet response latency, I'm going to select that and hit Start TV. The trace validation will analyze the entire trace and it will look for commands and responses in the trace. In this case, it will find all commands and all responses, and it will give you a latency measurement between them. So instead of having to manually measure the latency using cursors on each packet, you can run this trace validation test, and it will tell you what the command, response, and latency were. If you come up here and select a command packet, and then you put your bookmark on it, you can see that the latency between that command and that response was 1.069 milliseconds, which is what we are showing here as the latency measurement. But you can see also that we set a minimum and a maximum latency, and we can evaluate that to identify if something failed our criteria. So you can use trace validation to get latency measurements on a lot of different packets in the trace, but you can also set minimums and maximums. So that concludes our demonstration. If you have any questions, you can find more information on our website at protocolinsight.com. Thank you very much.